In order to set the system up in the spectral irradiance mode, we should connect the D7 input optic to the quartz fibre bundle, holding it in place with the retaining grub screw. Where the fibre bundle is not already connected to the IDR300, we should go to the software and initialise this time in the spectral irradiance mode. Wait until the motors have stopped moving before fitting the fibre bundle and locking it in place. We can have the CL6 set up with the red and black cables and fan cable, selecting 6.3 amps and powering on. And finally, adapting the D7 diffuser to the DAR of the CL6 before proceeding to calibrate in spectral irradiance. We will now turn to BEM Plus and initialize in the irradiance configuration. Where the fibre bundle hasn't been installed, we should wait to the end of this procedure. We will hear the motor stop moving and this initialization window will go away before we fit the fibre bundle, and now we can do so with no fear that it will impede the movement of the slits. We go to Scan Setup for this CL6 calibration measurement. Here we will use custom wavelength files to define the step size of the measurement. Normally, without custom wavelength files in place, the same step size would be used throughout the full start to end wavelength range. Here we would like to change the step size as we go through the scan range, and custom wavelength files are kept in this folder. For the CL6 calibration, there are two, both covering the range 300 to 1100 nanometers, which is the base range of this irradiance measurement with the CL6, the D7 diffuser, and the IDR300. The CL6 irradiance 300 to 1100 steps 2 nanometers to 400 nanometers, then 5 nanometers thereafter. In certain cases, for example with white LEDs where there's very little emission above 800 nanometers into the range of the low response silicon detector, it's desirable to increase the bandwidth to 10 nanometers or even more to try and increase the throughput and lower the noise equivalent irradiance. And it's for this reason that the CL6 300 to 1100 for white LEDs has been generated 2 nanometers to 400, to 800 nanometers, 5 nanometer steps, and then 10 nanometers thereafter. For the moment we will select the CL6 300 to 1100 custom wavelength file. We should go into advanced and ensure that data correction is not selected for this measurement, which is a system calibration. We should check, however, that auto range and zero calibrate are always selected. We need not touch those. In terms of number of spectra, I would typically select 10. The reason being that we need to allow for a lamp warm-up time, which we may say is 5 to 10 minutes. Effectively, what I would prefer to do is to switch the lamp on, hit new scan for 10 scans, leave the system to do the measurements, come back some short time later, and delete the first 5 scans, for example, say this is the lamp warm-up time, and we can take an average of the remaining 5 scans to provide the calibration of the system. It's also beneficial to take the average of a number of scans. It will give us confidence that this measurement is stable and the system is stable, and should there be any noise in the measurement, which we don't necessarily expect there will be, but should there be any noise, then averaging a few scans will average out the noise, which would otherwise appear, since this is the calibration measurement, in all of the future measurements done with this system. So now we've selected 10 scans and we select new scan, and we'll let power on now the CL6 at 6.3 amps with red-black leads and fan connected. As I say, the lamp is now having a warm-up time during which we're doing scans, and we can now go and do some other task. The zero calibration information will be reported in a short time. Here we're employing 2 detectors, the photomultiplier and the silicon photodiode, which will be reported, and the scan will commence. And we will pick that up in a short time at the end of the 10th scan to see how to deal with the results and to apply the system calibration. Now we've come to the end of the measurement. We can power off the 605 constant current power supply, and we should leave the CL6 for a minute before moving to allow the filament to cool down. Now we can inspect the measurement results. We can see the 10 scans. After 400 nanometers, an increase in the measured photocurrent because of the increase in bandwidth, and at 850 nanometers there's a discontinuity when changing from the photomultiplier with high sensitivity to the low sensitivity silicon photodiode. We can see some warm up here, some degradation in the lamp output, which we will take account of when we delete the initial 5 spectra. And if we right click logarithmic axis, we will see in the silicon region, and in fact the system has been set up to use the third in-gas detector from 1050 nanometers to avoid the band edge, the tail of the silicon photodiode, which has some temperature sensitivity as to the ambient temperature, and indeed a somewhat lower response to the in-gas diode on the single monochromator. This can certainly be changed to use the silicon to 1100 in the double monochromator mode. Now we should go to analysis, delete spectra, to delete the initial 5 measurements. We will say this is the warm-up time, OK. And now we will take the average of these 5 spectra. Analysis, spectral average, and we simply hit OK to have the average reported. And finally we will analysis, delete spectra, the initial measurements. So we're left only with one result, one scan, that is the average. And we can save that in the spectra folder as the irradiance of the CL6. Now, if the measurement region of 300 to 1100 nanometers only is required, we can directly apply data correction. We go to scan, data correction. The certificate file is the true calibrated irradiance file of the CL6, which is in BEMA Plus calibration folder, CL6. The system file is the average we just saved, the irradiance of the CL6, and we can hit calculate calibration data. Data correction is not selected. Do we wish to select it now? Yes. And we should save to file for future reference irradiance and today's date, the 29th of May 14. Now if we return to scan setup, in advanced we will see that data correction is applied. That is correct. And we should now perform measurements of sources under test. We should not change the custom wavelength files, since the IDR300 motorized slits are in auto mode, which means that the slit bandwidth, the slits are set to a bandwidth equivalent to the step size required. And changing the custom wavelength file, one changes the system bandwidth, one changes the throughput, and invalidates the calibration. We can perform 1 or 2 measurements of sources under test. There's no need for such a large number of measurements. Where a calibration in the UV is required, we should also look to calibrate the system with the CL7 deuterium lamp, which we will look at now before measuring any sources under test. Where measurements are required of spectral irradiance below 300 nanometers, then we must calibrate the system with the CL7 deuterium lamp. The CL7 deuterium lamp has its own dedicated 706 power supply, which is connected to the source via the red, black and blue cables, and we can simply, with the mains connection in place, power the 706 on. The power and starter LEDs will illuminate, and after a short time the heater will cease to be applied solely, and the lamp discharge will be obtained. We can see the starter light has gone out. We shall have UV emission from the source, and we can now connect the D7 diffuser to the DAR of the CL7. And now we can proceed to look at the measurement in Bemin Plus. Now if we look to Bemin Plus, in normal circumstances one would perform, if a measurement 200 to 1100 is required, the calibration of the CL6 followed directly by the calibration of the CL7 or vice versa, without applying data correction in between. I demonstrated the use of data correction where only the CL6 calibration is required. I must switch this off in order to perform the calibration of the CL7 lamp 200 to 400 nanometers. A custom wavelength file is provided for this calibration, although not actually required, since the step size of 2 nanometers is applied throughout the range. And we will select another 10 spectra to allow for lamp warm-up time and ensuring that the system is stable. Now we hit new scan, and we will only see the zero calibration data of the single photomultiplier, since it is the only detector included in the spectral range of this measurement, and the 10 measurements will advance, and we will pick that up at the end of the scan. Now we have come to the end of the 10 measurements, and we can power off this 706 power supply. We need not perform the average calculation as we have shown previously with the CL6, for this will be done by a separate utility. We must, however, delete the initial 5 spectra taken as those during the lamp warm-up, and indeed by inspection one can have a look at the stability of the measurement. Here I would also suggest that the 6th spectrum hasn't stabilized, so we delete that as well. And I will save these results as the irradiance of the CL7. Now, I don't take the average because we need to find a manner of generating for both the CL6 and the CL7 calibrations one continuous data correction file. In the scan data correction, we can see that only one lamp, one measurement of the lamp can be accounted for. And it's for this reason that we have in utilities the correction calculator. So the correction calculator effectively generates the cal file, so the ratio of the certificate file of a lamp divided by the measurement of that lamp. We have 2 lamps, CL6 and CL7, and we load the 2 spectra, one of which we presume is absolute and the other relative. In general, we take the CL6, the quartz halogen lamp, as the ultimate calibration standard. Passing a current through the filament today, tomorrow, or the next day will result in the same irradiance produced at a plane of calibration. In the case of the deuterium lamp, since it's an arc lamp, then one can imagine that striking the lamp from time to time, the arc establishes in a different location, so the overall irradiance may change, but one presumes that the spectral shape remains constant. And it's on this basis that this correction calculator operates. We have performed measurements 300 to 1100 with the CL6, and we will indeed load these measurements up and the corresponding calibration file. And we have performed measurements of the CL7 200 to 400, thereby having an overlap region of 300 to 400 nanometers. And you can see here, in the case of the CL7, for which an average wasn't generated, this utility determines that multiple spectra were found, and do you want to take an average? Okay. And we load the certificate of the CL7. The absolute spectrum is always the CL6. We ensure spectrum 1 is selected as absolute, and we can show overlap. This window shows the resultant calibration file for the two lamps, and the green line the ratio of the two. And we typically take a midpoint as being the crossover point. So effectively, the calibration file for the CL6 from 352 up is maintained. We adopt the calibration file of the CL7 below 352 nanometers, but adjust it to a level to match the CL6. And 352 is where the software always tends to find the best crossover point, and we can hit Save Correction File, and we'll call it Irradiance 200 to 1100 nanometers, and we can add today's date for future reference. And the process is complete, except for one final step, and we can close this without saving. We need to go to Scan Data Correction to load that calibration file, this new calibration file. Data correction is not selected. Do you wish to select it now? Yes. And actually, one final step is to modify the custom wavelength file, because now we are measuring 200 to 1100 nanometers. So in the custom wavelength files folder, we will find two Irradiance 200 to 1100 nanometer custom wavelength files, one to correspond with the CL6 Irradiance that we used, and one to correspond with the CL6 for white LEDs. We used the CL6 300 to 1100, so we should use this one. And we can now proceed to measure sources over the full range, selecting one or two spectra in the measurements. Now we will look at the measurement of the MR16 lamp that we looked at previously and determine the irradiance produced by this source. We will now proceed to measure the irradiance produced by the MR16 source. According to IEC 62471, in its current status, sources should be measured at a distance commensurate with the application. GLS sources, General Lighting Service sources, should be measured at a distance at which the source produces an illuminance of 500 lux. Indeed, they need not be measured at that distance, but one must at least report at that distance. For all other applications, non-GLS, we should measure 200 millimeters from the apparent source. In order to determine the 500 lux distance, which is effectively really only used in reporting for the main part, we have the DH400VL photometric detector with a virtual lux meter in BIM+. The DH400VL consists of a 7mm diameter cosine corrected diffuser with a close match photopic detector inside. The generated photocurrent being measured by the amplifiers in the IDR300, and communication being obtained with the BIM+ through an add-on or utility. For the first use, the cap should be placed on the lux meter for the purposes of dark measurement, and thereafter we can simply proceed to use it as normal and determine the distance at which the source produces 500 lux, and we will look at BIM+ to see the results on screen. One should measure the illuminance, the lux level, at the direction of maximum illuminance clearly, and determine the 500 lux distance. In order to view the illuminance measured by the photometric detector, we go to Utilities, Meter. For the very first use, one should perform a dark measurement by ensuring the cap is placed in front of the photometric detector, hitting OK. And the dark current measurement will be performed and saved to file and will not need to be performed in the future. At the end of this procedure, the PSL system will save these parameters to file, and we will be presented with the illuminance read by the photometric detector and amplifier system. if we remove the cap, we will see the illuminance will be red and a short delay will be experienced as the amplifier ranges, and we can in this manner determine from the source the location of 500 lux. And note that measurement distance. Whether the source to be measured be a GLS or non-GLS source, I would typically measure at 200 millimeters. In this manner, I can effect an analysis of non-GLS and use the data to scale to 500 lux to report as a GLS source. The only fine point that one must consider is that if one does really wish to follow the route of non-GLS, one should also pay attention to apertures, as we will look at shortly. The measurement distance should be 200 millimeters from the apparent source location, which for the source we have determined as effectively the front plane, and we can measure 200 millimeters from the front of the diffuser to the front of this source, and use the alignment utility in the software to adjust the lateral and vertical position to obtain a maximum. Here, as opposed to spectral check, we really are concerned with a maximum value because we're now analysing the worst case scenario at 200 millimeters. Now, this irradiance measurement will be used to evaluate the UV hazards, the actinic UV and near UV hazards, and the blue light exempt risk group as well. And the measurement into the infrared will be used where infrared measurements are required to evaluate IRI and thermal skin hazards. With regards to the blue light hazard, there are two cases: blue light small source and blue light standard. Where the source obtains an angle less than 11 milliradians, a simpler irradiance measurement be required for the measurement of the blue light hazard. In which case, no further action need be taken. One simply measures as we have organised here. Where the source is larger than 11 milliradians, then one must pay attention to the apertures required in the measurement of blue light radiance. This will be described in more detail in another presentation. Essentially, the blue light exempt risk group should be performed over a measurement field of view of 100 milliradians. And in performing the measurement at 200 millimeters distance, we should place an aperture of 20 millimeters diameter at the source. Clearly, where the source is smaller than 20 millimeters, then one need not place an aperture there. And this introduces a complexity in the evaluation of sources which are larger than 20 millimeters, which are for GLS applications, since should one also want to effect a non-GLS analysis, one should consider the apertures and perform measurements with the apertures in place. So for example, one may need to perform a measurement where this source larger than 20 millimeters, one should perform a measurement without an aperture in evaluation of UV hazards, provided that the source is not larger than 1.4 radians, which is another stipulation for the evaluation of the UV and IRI hazards. And if one wishes to consider the blue light hazard, one should repeat a second measurement with a 20 millimeter aperture in front of the source, aligned for maximum throughput. And we can use the alignment utility to help in the alignment of that. In the case here, the source subtends greater than 11 milliradians, so it's not a blue light small source, but in fact the array of LEDs is just smaller than the 20 millimeters, so it is smaller than 100 milliradian field of view and no aperture is required. So we will now proceed to align the maximum signal and then perform a measurement. Having set the source 200 millimeters from the front face of the D7 diffuser, we can align the source using the alignment utility. And for this white light source, 555 nanometers will be a suitable wavelength at which we can do this. Hit go to set the monochromator to 555, and we will read the signal, and we can then adjust the position after the amplifier has ranged to obtain a maximum. And we should pay attention again to the direction of the peak intensity emitted from the source, and we should pay attention to obtaining as high a value as possible, since as opposed again to the spectral check relative measurement, we are now performing an absolute measurement which will form the measurement result for this source. The maximum can be reset where one desires. If one, for example, goes too close to the source and amends the measurement distance, the maximum will be incorrect. And when one is happy that a maximum is obtained, we can close the alignment utility and proceed to measure. And here I'll simply perform one scan. We ensure that data correction is selected, and we hit new scan. And we can see now that on the y-axis, irradiance in milliwatts per meter squared per nanometer is now shown because calibration is applied, and we are returning the absolute irradiance of the source. And we will pick this up at the end of the measurement. Now, at the end of the measurement, we can see the measurement result. The absolute irradiance produced by this source at 200 millimeters from the source, here showing this 405 nanometer LED pumping a phosphor. It's an unusual technology. And we can see very little signal in the UV and in infrared. And if we right-click logarithmic y-axis, we can see indeed the system is measuring effectively noise in the UV to 380 nanometers, and it's starting to become noisy in the infrared because there is very, very little, if any, emission in that region. One can see also to the right-hand side integrals reported. These integrals are useful to inspect, although one need not do this since the PSL wizard will perform all calculations required. The actinic UV exempt risk group limit, for example, is 1 milliwatt per meter squared, and we can clearly see we're well below that level. The blue light hazard exempt risk group is around 780 milliwatts per meter squared, is a radiance limit converted from the 100 watts per meter squared per radian radiance limit, and we can see we're above that level. Now, in this case, this MR16 LED, we didn't need a 20 millimeter aperture to perform a 100 milliradian measurement of the source, and therefore this source fails exempt risk group. Were this a larger source for which I ought to have performed a measurement with a 20 millimeter aperture, but in the first instance did a measurement with no aperture in place, and see that the blue light level is below 780 milliwatts per meter squared, then in measuring the whole source, since I'm below the limit, clearly in measuring with a 20 millimeter aperture in place, I would be equally below the limit. And one can use this as a means to not have to do this 20 millimeter aperture measurement, which may be difficult in terms of aligning the aperture and placing the aperture in front of the source. Clearly, if one measures a larger source and in the first instance evaluates the UV with no aperture in place and finds that the blue light hazard is above the limit significantly, and we expect that, for example, placing an aperture will not reduce that limit significantly, then one must perform the measurement with a 20 millimeter aperture in place. I often use a quick calculation based upon the size of the source or the number of LEDs within a 20 millimeter diameter area compared to the entire array to give me an idea as to whether or not the blue light hazard will reduce sufficiently to become exempt or not. The illuminance here reported is 8,546 lux. And the PSL wizard will normalize to a level at 500 lux for GLS sources. But we can also do it manually. But before that, we will save this file for reference, IRR MR16. IRR MR16. We can simply calculate the difference between the 8546 0.6478 divided by 500 lux to determine the scale factor. We copy that, and we can go to analysis, spectral arithmetic, and we can divide the current spectrum operand A by a constant, which constant is indeed the value we've calculated. And the replace operand is selected, so that when we hit OK, we will have effectively the results at 500 lux, and we may, if you wish, save that as the irradiance of MR16 at the 500 lux. We can report on that basis. And at 500 lux, we can see the blue light hazard is below the 780 milliwatt per meter squared effective limit, which is what we would expect for a GLS source. Now, treating this MR16 as a non-GLS source to go forward and to look at other measurements, we will see, according to the PSL wizard, that the next measurement required is an irradiance measurement in consideration of the risk group 1 blue light hazard.